Okay, so welcome everybody. Today's speaker is Patrick Serwene from the University of Dresden, and he is going to talk about reduction theorems for generalized block fusion systems.
Yeah, thank you so much for to the organizers to giving me the opportunity to stay here at the Isaac Newton Institute, and also in particular to give a talk today. So as Rada said, I'm currently with the TU Dresden in Germany. I'm a postdoc, and before that I was a PhD student of Rada, and also all of the stuff I'm going to talk about today was our results of my PhD thesis. So yeah, I'm very interested in fusion systems, and in particular, today I'll speak a bit about generalized block fusion systems. So for the entire talk, I will fix P to be a prime, take an algebraically closed field, characteristic P, and G finite group for now. And I think most of you already seen plenty of times what a fusion system is, but I'm gonna define it anyways again. So the category F whose objects are the subgroups of a P group P, and we call this category on P. Is a fusion system if for all QR subgroups of P, we have the following assumptions for their morphisms. So we look at the morphisms at homomorphisms between Q and R. So first of all, we only consider injective group homomorphisms. And secondly, if we look at the homomorphisms between Q and R that are induced by conjugation with an element in P, I write it like this, and this needs to be contained in here. If P is a morphism in F, P needs to be a composition of an F isomorphism and an F inclusion. And lastly, composition of morphisms is as usual. So it's the usual composition of group homomorphisms. Okay, so if we have a category which fulfills all these assumptions for F fusion system, but the categories we get like this, they're too general. We need two more technical axioms. And I will not write it down, I'll just tell you their names. It's the silo and the extension axiom. So in the fusion system, which also fulfills these, is called a saturated fusion system. And the convention for this talk will be that I drop the term for convenience. So whenever I say fusion system, I will actually mean saturated fusion system. Okay. So, okay, this is nice. So we have a category, but so why should you be interested in those? Well, they have applications in several disciplines of algebra. Firstly, in group theory, there's something called Aschbacher's program. And then the idea is to use two fusion systems on two groups, to simplify the proof of the classification finite simple groups. So there's something called, so the normalizer of a two group is called a two local group, and those two local groups can have two prime normal subgroups, and they cause some issues in the proof. But by using fusion systems, when we can get rid of these problems. Then also in topology, in particular homotopy theory, they are interesting because fusion systems provide or induce P-completed classifying spaces. So they are interesting for homotopy theorists also. And then in particular, where I'm coming from, local global conjectures, the representation theory. And I will say a few more words about this last application on fusion systems when I tell you a bit about the main conjecture that I'm working on. So now we've seen the definition of fusion systems, we've seen some applications. So now let's look at some examples of fusion systems. Well, the most hands-on example is we do the following: we take a finite group G, we take a Stylus subgroup of G, we then define FGG to be the category on P with homomorphisms or two subgroups U and R of P to be just the conjugation maps induced by an element in G where it's well defined. So that means it's all conjugation maps from Q to R where it's well defined. So G acting on Q needs to be in R. So then we can show that this is a fusion system, but not every fusion system is of this form. If a fusion system arises in this way, we call it block realizable. We call it realizable, sorry. And otherwise, so if we cannot find a finite group with a Stylus subgroup such that we have that the fusion system is equal to FPG, we call it exotic. So, and this way, fusion systems arise from groups, and they can also arise from blocks. And for this, I need to introduce some notation. So, so we take again G to be a finite group, and then a Brouwer pair for G is a pair UEQ where Q is a P subgroup of G and EQ is a block of the centralizer of Q in G. Yeah, I'll do it up. See how this works. What about this? So, okay. Yeah, so we will see that blocks also induce fusion systems in quite a similar way. And so the natural question will then be, how are these two ways of getting fusion systems related? Split it here. So now also for a P subgroup of G, we define the following map. So we take an A, an arbitrary element in the group algebra, AG, and then we define, so maybe for A in the group algebra, we define the Brouwer map of A, and here we need to specify G and Q. And so what does the Brouwer map do? Well, we just take this element and forget everything which is not in the centralizer of Q in G. So we just take the same element, but here we just run over all G in the centralizer of Q in G. And so this is called the Brouwer map. And if we restrict this to the few fixed points, we actually get a homomorphism, which is then obviously called the Brouwer homomorphism. Okay? And so with the help of this map, we can define partial order on Brouwer pairs. And it should also be stressed that if we, so in particular, we can look at the following situation. We take B to be a block of KG, and then a pair QEQ, such that we have 1B is less than or equal to QEQ, is called a B-Brouwer pair. So with this setup, we're ready to define fusion systems of blocks. So we take B again, be a finite group, B a block of KG with maximal B-Brouwer pair P. That also means that P is a defect group for B. Define F, P, E, P, G, P to be the category on P with homomorphism maps could be again all the maps that are induced by conjugation with elements in G, where it's well defined. So here this translates to having that G acting on QEQ needs to be less than or equal to RER. And yeah, for obviously for subgroups Q and R of P. Yeah, and again, not every fusion system. So first of all, I should note that this is a fusion system. But again, not every fusion system needs to be of this form. A fusion system which can be written in this way is called block realizable. A fusion system which cannot be written of this form called block exotic. So yeah, now obviously the natural question is, we have these two ways to get fusion systems, realizable and block realizable. How are they related? And there's a very important theorem by Brouwer, which already answers one direction immediately. So if we take G to be a finite group, we take B, principal P block of Kg with maximal B Brouwer pair PEP. Well, then it turns out that P in this case is a Sylow-P subgroup of G. And if you look at the category FPG, then this is the same as the category FPEP PP. So in particular, this means we can take any realizable fusion system and write it as the fusion system of a principal block. So this means realizable implies block realizable, or in other words, block exotic implies exotic. All right, so what about the other way? Well, that's exactly what I spent basically all of my PhD thesis spending evidence for. So the conjecture is as follows. So we have F fusion system on P. Then we conjecture that F exotic implies F block exotic. So this conjecture has been around for, I think, over 20 years now. There's still, and I mean, most people are convinced that it's true, but we're still a long way from proving it. But I can tell you a little bit about some progress we did recently. And I'll also tell you for which groups it's known to hold. So if P is abelian, the conjecture is true, and the reason is there's just no exotic fusion systems on abelian groups. If P is extra special of order P cubed, it's also true by, and it has been in the paper by Rada together with Radu Stanko in 2008. And if P is a Sylow-P subgroup of G2, P to the n, or P is a Sylow-P subgroup of P is U4, P to the n, for any natural number n is also true. And that's, so Chris Parker and Jason Cimararo, they classified all fusion systems on Sylow-P subgroups of G2P with some assumptions, and they found some exotic systems. And for those exotic systems, I proved that they're also not exotic. And then actually Martin van Beek, he extended their classification to include all of these groups, and he didn't find any other exotic ones, so it holds now for these groups. Okay. So, but I mean, this is all nice, but there's still not really, we don't really have very good reduction theorems yet. So far, no real strategy to prove the conjecture. So far, what has been done is just to like look at the family of exotic systems at a time and deal with them at a time. And there's another problem actually when one wants to do this, because block fusion systems sort of misbehave with respect to Clifford theory. So if I take a normal subgroup of G, and I take C, a block of Kn, which is covered by a block B of Kg, that means BC is non-zero. So it's like the block of K lying over the block of N, sort of. And so now if you take P, a defect group for P, then we have that P intersected with N is a defect group for C. So far so good. But the fusion system of C does not need to be contained in the fusion system of B. So the fusion system of B can be smaller than the fusion system of C, and that's very unsatisfying from a group theory point of view. And in particular, it also doesn't allow a descent to normal subgroups. But that's where the category for my title comes in. You can circumvent this in a way by using generalized block fusion systems. And this is a very long name, so I will just call them GBFS for now. Okay. Any questions so far? Okay, so now we define generalized block fusion systems. So we take P to be a finite group with a normal subgroup N, and C shall be a G-stable block of Kn. Then we define a maximal CG Brouwer pair to be a pair QEQ such that Q is again a P subgroup, and here it's careful, so it's a P subgroup of G, such that also we have that the Brouwer map with respect to N and Q of C is non-zero, and EQ times Brouwer map of N and Q applied to C is non-zero. And of course, EQ is a block of K, C, N, Q, such that this holds. So the difference to block fusion systems are very slight, but there are differences. So first of all, a maximal, so the first component of a maximal CG Brouwer pair is not a defect group for a C, because in particular, it's not even necessarily a subgroup of N, it lives inside the bigger group G, but we still apply the Brouwer map with respect to N, and this block still lives in the centralizer of Q with respect to N. Okay. And so now we can define generalized block fusion systems. We take PEP, so we just keep the notation. We take PEP to be a maximal CG Brouwer pair. Then we define F, PEP, G, and C to be the category on P with homomorphism maps. Again, the conjugation maps between Q and R for subgroups Q and R of P. where this is well defined. So we call this fusion system of this form we call generalized block fusion system. So first of all, this category is fusion system. And the fusion system of this form we call generalized block fusion system. Okay, so this, I mean, it looks very similar to block fusion systems. So why should this be any better? Well, these generalized block fusion systems, they behave better with respect to normal subgroups. There's some very useful relations, which I will tell you about. And it should also be noted that every block fusion system, in the old sense, is a generalized block fusion system. And we can see this simply if we set G and N to be the same. So note every block fusion system is a generalized block fusion system. You can see this if we set G to be the same as N in the definition. Okay, and now these generalized block fusion systems, they have some useful relations, and this has first been proven also in the Kessler-Stanko paper, but it has been slightly improved in Aschbacher, Kessler, Oliver. So it goes as follows. So we take G to be a finite group with a normal subgroup N, and C is a block, a G-stable block of Kn, covered by block B, Kg. Then if P of the PEP is a maximal P for our pair. So here I mean the old sense, so P is a defect group for B. Then there exists a maximal CG for our pair S, E, S prime, such that P is contained in S if we intersect S and P both down to N, they're the same. And P intersected N, E, S, N, P prime is a maximal C broad here. So P intersected N is a defect group. See, and further, the most important thing to take away is that we have the following relations. So we have that F, S, E, S prime, G, and C contains both F, P, 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 B, and F, S intersected N, E, S, N intersection prime of NC, and this one even as a normal subsystem. So both the fusion systems of the block fusion systems are both contained in here, and so this allows us to have a descent to normal subgroups. So we can use this, and it has been used already in Kessler-Stanko paper, and also when I was dealing with the systems specified by Parker-Semeraro, I also used these relations. And since they form a little triangle, I always call them the triangle relations. So yeah, we see clearly generalized block fusion systems could be useful. And so now I actually think that maybe we shouldn't study the old conjecture so much, but we should maybe just study this conjecture for this more general category. So the conjecture would be then that every generalized block fusion system is non-exotic. And so Okay, so what's the first step is then to see whether broad third main theorem also holds for those, and it turns out it does. So if we look at this, we take G to be a finite group, normal subgroup N of G, and C the principal block of Kn with maximal CG raw pair PEP, and P is a Sylogy subgroup of G, and the fusion system F, P, E, P, G, and C is the same as the fusion system F, P, G. So that's one first step. And then there's two other key results, which are very elementary to study block fusion systems, which I also managed to generalize to generalized block fusion systems. So they're both due to form. So they're called the first and second form reduction. So for the first form reduction, I need to recall a certain subgroup of G. So again, I take N to be normal in G, and then I define the group IGC to be basically the stabilizer of C and G. So that's all G and G, such that G acting on C is just C again. And then we actually have that there is a one-to-one correspondence between the blocks of G covering C and the blocks of IGC covering C. And so we normally, if this block would be called B, we would call this block B tilde, and we would call B tilde the form correspondent of B in IGC. Okay, so this is the point of the first form reduction, which I will tell you about right now, is that we can, instead of studying any fusion system of a block, we can always change to this IGC, which is called the inertial subgroup also. So we can always assume stability. So this is another theorem which I proved in my thesis. So we take again take F to be a fusion system on P. Take G, a normal subgroup of H. So they're both finite groups. And we take N to be a normal subgroup of H. It's also contained in G. And C, we take, we take B to be an H stable block of KG, covering a block B of Kn. And then if we have that F is equal to FPEP HGB, we also have that F is equal to FPEP prime IHC IGC B tilde, where B tilde is the form correspondent. B and P tilde is a maximal B tilde IHB broad pair. So yeah, instead of studying this fusion system, we can study the fusion system of the inertial subgroups. And in particular, so in the case where H and G coincide, that's the original first form reduction. Okay, so this is the first form reduction, so it's got to be also another one, maybe. Yeah, I'm not disappointing here, I have also other forms reductions of the second form reduction. And so what's the idea here? So let's just go back to just thinking about groups. So if we have a normal subgroup of G, and we have that P part of N is 1, then, and we have that S is a style of the subgroup of G, then if we identify the image of S under the canonical surjection to G modulo N with S again, and of course S is also a style of the subgroup of G modulo N, and it also holds on the fusion system level. So FSG in this case is then also FSG modulo N. And now we want to somehow have an equivalent or the corresponding result for blocks. And for blocks, having trivial P part just means having trivial defect. And this theorem is quite a handful, so bear with me. So we take again G to be a normal subgroup of H, such that the index of G and H has trivial P part. And we take N to be a normal subgroup of H, which is also contained in G. Then we take C to be an H stable block of Kn of trivial defect. So the defect group is just a trivial group. Then we take D and H stable block of Kg covering C with maximal DH broad pair PEP. And now the result tells us that there exists a P prime central extension H tilde of H modulo N, a block D tilde of K G tilde with maximal D tilde H tilde broad pair P tilde P tilde such that P tilde and P are isomorphic. G tilde is the full inverse image of G modulo N in H tilde such that D tilde is H tilde stable and the fusion system FPEP HGP is isomorphic to the fusion system F P tilde EP tilde H tilde G tilde D tilde. Okay, so yeah, it's quite a handful. I should rather say mouthful. So what does it mean? Well, it tells us how far we can and how far we can kick out N of the picture. Okay, so how much time do I have left? Like 20 minutes? Okay. All right. So for the remainder of my talk, I'm going to speak a bit about the strategy to prove the conjecture. So I mean, at some point, it's clear that we need to use the classification of finite simple groups and prove that it holds for all blocks of simple groups or quasi-simple groups. And so where are we there? Where are we at? So obviously, if the group is abelian, I don't have to say anything else. If the group is alternating group or the cover, it's also known to hold. If the group is sporadic, it's in David Craven's book. He proved it that the conjecture holds. And if that brings us to groups of Lie type, and if we are looking at groups of Lie type and defining characteristics, so that it's over a prime of P, it's also true because in this case, defect groups are either trivial or Sylow P subgroups. So this brings us to surprise groups of Lie type in non-defining characteristic. And for those, Mark Cabanes proved the conjecture, so the conjecture for block fusion systems. If P is at least 7 and block is unipotent, and if you don't know what unipotent means, I will explain it in a bit because I have to give a little bit of background. Talk about this first.
The first conjecture.
Yeah, I should maybe conjecture 1. So the old conjecture, which has been around for a while. Yeah. And so, I spent a lot of my PhD trying to somehow see what you can do for general blocks. And here I achieved an extension when using the generalized block fusion systems. Yeah, so theorem goes as follows. So we take P to be a connected reductive group where it's Frobenius F. And then F stable levy of G. So I should also say that for the rest of my talk, G is no longer a finite group. Yeah. An F stable levy with unipotent block B, and then we have some group N, which is contained in the normalizer of this levy, which is also F stable. Now we assume also still that P is at least 7, that the index N modulo L is the P part is 1, and that B is NF stable, and PEP, a maximal B NF Brouwer pair. And we have that the fusion system, generalized block fusion system FPEP, NF, NFB is non-exotic. Yeah, so it's an extension of Cabanes' result, and I don't use his result directly. I use the same results he uses to prove the result, but not his result directly. So it gives an alternative proof. And so, of course, this looks a little bit random, this group N, but there's reasoning behind it, and I will expound a bit on it now. So if G is a connected, reductive, algebraic group over some here at FQ bar, where Q is co-prime to P, prime power, F and P to G Frobenius, and L again F stable levy. then I can look at the Lustig reduction. So RGL is maps from the generalized irreducible characters of L to the generalized irreducible characters of G. And I will not write down how exactly the map looks, because then I would need to introduce a lot more notation. And it should also be stressed out that this map always depends on a parabolic subgroup in which the levy is contained. But for all that I'm doing, it doesn't depend on the parabolic subgroup. So I will just not write it down. And so we can use this. So if L is a maximal torus, you can use this map to parameterize the irreducible characters of GF. And so how does it work? So first, let's fix an F-stable torus of G so that we can talk about some duality. So we assume that G is dual to G star F. And now we have that there is a one-to-one correspondence between the GF conjugacy classes of pairs T theta, where T is a maximal F-stable torus of G, and theta is an irreducible character of TF, and the G star F classes of pairs T star S, where also T star is an maximal F-stable torus, and S is an element in T star. And T star F. So this is now the base, or this is used in the following very important theory due to the Lustig. So yeah, we take S to be a semi-simple element of G star F, and then we denote by G EGFS the irreducible components of generalized characters R T G theta, where T theta corresponds to T star S in this bijection above. And then we get that we have a partition of the irreducible characters of G into these classes, E, G, F, S, where S ranges over semi-simple classes in G star F. Okay. Okay, so I have 10 more minutes. That's perfect, actually, because now I'm also arrived at my final remark. So yeah, we can use these semi-simple elements to describe the irreducible characters of GF. And there's been some work by Bonafé, where they actually construct a group which has a fusion system which also uses this parameterization, and they construct a group which corresponds to the fusion system of any block. Okay, but I'll write this down and we'll come a little bit clearer. Okay, so we can assume that GF is in duality with G star F, and now we take D to be a block of GF. And now there exists a semi-simple element in G star F. There has to exist a semi-simple element in G star F such that irreducible characters of G belonging to the block D intersected with EGFS is non-zero. Oh, I remembered I promised you to tell you what the unipotent block is. So, okay, so if you look at this, so what's the most easy simple element? Well, that's 1. So if we set 1 in here, the characters that we get are called unipotent characters, and the unipotent block is just a block containing at least one unipotent character.
I think here you maybe want P prime.
Semi-simple P prime element. Yes. Thank you. Okay, and now we take a levy G star, levy L star and G star, which is minimal with respect to containing the connected component of the centralizer of S in G star. And we denote its dual by L. And then the result by Bonafé-Rouquier. So they prove that in many cases, not always, but in many cases, the fusion system of D is equivalent to the fusion system of a block of a subgroup of GF containing LF as a normal subgroup covering covering a unipotent block LF. And so now I can use my theorem, which is up here, to prove that the generalized block fusion system related to this normal extension is non-exotic. Okay, so again, to summarize it, so Bonafé-Rouquier, they construct a group which lies between LF and GF and contains LF as a normal subgroup, such that the block of this group they construct as a fusion system which is equivalent to the fusion system that we were originally interested in, and this block also covers the unipotent block of the fixed points of the levy. And here I can use this theory to prove that the fusion system, generalized block fusion system associated to this extension is non-exotic. But there's still, I mean, we're still not done here because, so we know now that a fusion system isomorphic to the fusion system of D is contained in here, but it still doesn't mean that it's also non-exotic. Yeah. So there's still work to do, and there's still this gap to close, but it's some steps towards proving the conjecture. And that's all I wanted to tell you about today. And thank you so much for your attention.
Questions?
mean, there's no sort of reduction to almost simple groups here, is there?
No, unfortunately, we don't have something like that yet.
Is it true even for solvable groups?
Yeah.
It is.
Yeah, there's a second form reduction. example.
Oh, yeah.
Just
right.
out.
Okay, sure.
They're all non. But yeah, and you have to use the model theorem, I guess.
Yeah.
So as for the first conjecture, are you trying or plan to try with other family of exotic fusion systems?
There's a few that I have on my radar where I can try some similar techniques to what I did for the Parkinson-Rohr systems. Yeah, there's, for example, the exotic subsystems of fusion systems of the general linear group, and there's some other ones where I'm thinking about trying to see it for them too.
I was thinking of the Parker-Strott one.
Yeah, exactly. Parker-Strott and also Parker-Cleland. Yeah, some are they're on my radar.
Any other questions? No, there don't seem to be. I guess we don't have anything remote. Okay, well, all right.
Remote watchers even.
Yeah.
Yeah. Oh, nice.
Oh.
Very nice. Yes.
Very good. Okay, so there seem to be no further questions, so
Okay.
let's thank Patrick again. Lunch.